Okay, so Mukund Rangamani is going to talk about extremal black hole thermodynamics, the view from afar.
Great. Thanks, Pranay. Apologies, everyone. I would have liked to come, but I just started teaching yesterday, and it's impossible to get away to some double teaching. So I was requested to review some stuff by Pranay on black hole thermodynamics, especially extremal black hole thermodynamics. And I'll sort of begin with a broad motivation and spend some time on an older paper about the extremal Kerr black hole. But I'll try to get to something more recent, which I did in the fall with other people, at least flesh out some of the results for you. Okay, so roughly the plan is to talk about two papers, one both with my student Ilya Rakic and collaborator Joaquin Turiachi from Washington, and the second paper also with Don Merolf and a fantastic UCSB postdoc, Maciek Kolanowski. So the question that we were trying to answer, and the question that has been answered by other people in the last 5 years or so, is for a long time, there's been a sort of puzzling situation that if you look at extremal black holes, especially non-supersymmetric extremal black holes, classically they have a non-trivial degeneracy at zero temperature. Yeah, it's a bit curious statement. It's usually formulated as statement that it seems to naively violate the third law of thermodynamics, but this is not something that per se bothers me, but there's a serious issue which was pointed out nearly 3 decades ago, namely, it does pose challenge for how near-extremal black holes Hawking radiate. So around any extremal black hole, if you go to a near-extremal black hole and expand the thermodynamic parameters in powers of temperature, you'll find that the energy scales quadratically away from extremality, whereas the entropy scales linearly. So since the energy scales quadratically away from extremality, at very low temperatures, the black hole doesn't even have energy to emit a single Hawking quantum. So this is a problem pointed out in 91 by these folks, pointing out that there's an issue with how extremal black holes would Hawking radiate out their charge. And this has bothered many people, and there have been various issues, various attempts to resolve this puzzle in the intervening decades. Then the interesting statement that one can make is that now we understand what's happening, at least in this case of non-supersymmetric black holes, namely they behave like conventional quantum mechanical systems with a few low-lying excitations and perhaps not this macroscopically large degeneracy that we see classically. And this came out of work done initially by Ghost, Maxfield, and Turiachi, and then in an impressive paper by Iliescu and Turiachi in about 4 years ago. The point that these folks emphasized is that when we try to do the Gibbons-Hawking calculation for black hole thermodynamics, that semi-classical analysis that we use where we evaluate saddle point actions of the gravitational path integral has to be carried out with care. It's true that the black hole is a dominant saddle, but in the near-extremal regime, it's not true that the saddle point answer itself is sufficient. In particular, the one-loop determinant of certain modes around this saddle are important. Taking into account this one-loop determinant gives the following general formula for what the near-extremal black hole thermodynamics ought to be. And the way I've written this is basically I've written the partition function evaluated around a single black hole saddle. S0 would be the classical Bekenstein-Hawking entropy formula for the extremal black hole. There's the linear correction away from extremality, which is governed by S1. There are logarithmic corrections to entropy that various people have studied over the decades. They come from quantum fluctuations of massive modes. But there exist massless modes or nearly-gapless modes in the near-extremal limit, which give you a prefactor that scales with a positive power of temperature. Okay? And this one-loop determinant of these gapless modes sort of brings down the partition function. And therefore, at some point, although I'm going to say that the black hole degeneracy goes to 0, at some point, the black hole saddle may not be the dominant saddle, and some other saddle maybe the saddle indicated in the previous expression by I1 takes over. In general, we don't know what these saddles are and what other geometries could contribute. But what is clear is that there is a suppression of the classical degeneracy to the point where we might expect that the black hole starts to behave more and more like an ordinary quantum system. So the way the calculation was done, which I'll explain, was by looking at what the zero modes are in the background of extremal black holes and how their contribution can be accounted for in this path integral calculation. One way to think about this is to realize that all extremal black holes have an infinite ADS2 throat with an enhanced SL2R isometry in the near horizon region. One can sort of intuitively say that we can just go down this throat and dimensionally reduce to this ADS2 spacetime and use ideas that have been made that have been in the context of that have been discussed in the context of GT gravity, where you can evaluate the one loop determinant and take into account the quantum effects of the modes that exist in this near horizon geometry. Alternately, as I will describe, one can just work in a full geometry and deduce that the quadratic fluctuation operator around the saddle has a set of zero modes. Okay. And for certain cases, like rotating black holes, this dimensional reduction prescription and using effective JT gravity is not the most sensible way to proceed. One has to actually work in the full geometry. Okay. And that's what we did in a paper in our first paper with Ilya and Joaquin. And I should also point out that this was done concurrently by the Harvard group folks. All of these analyses basically zoom into this near horizon region and exploit the ADS2 factor to identify the zero modes in question. In fact, the zero modes in question are not something new. They were known from the old days from the work of Camporici and Higuchi, and were exploited to great extent by Sen in his analysis of one-loop corrections to black hole entropy. The one piece of information that Sen did not fully use was that he was aware that there are these gapless modes, but he made an assumption that these gapless modes contribute a finite one-loop determinant, but it turns out that they actually don't contribute a finite one-loop determinant, but rather give you this temperature-dependent power law. Okay. Once one identifies the zero modes, there's a nice way to compute their contribution to the one-loop determinant, and one can just work in the near-extremal limit using a small temperature regulator. And all of this can be done by staying in the near horizon region. So in some sense, this whole discussion of what's happening to black holes and their near-extremal thermodynamics is something that you can do by just going down the ADS2 throat of extremal black holes, sort of allowing yourself to identify what the zero modes are, turning on a small temperature to sort of gap out these zero modes so that they're not gapless, but nearly gapless, and then using that regulated answer to compute the one-loop determinant. Okay. This is somewhat unsatisfactory, and this is where our second paper was born out of. And the sort of unsatisfactory aspect of this was that it's not clear a priori where these quantum corrections are coming from by just looking at the near horizon, but rather you might want to ask what is happening in the full geometry that allows us to see these quantum corrections, these temperature-dependent corrections to the black hole thermodynamics. Okay. And the idea here is not to make explicit use of the ADS2 factor at all. Okay. So, for example, in the original paper of Iliescu and Turiachi, the way they did the calculation was they looked at extremal Rice-Nordstrom, and they broke up the geometry into the near horizon and far regions and did some matched asymptotics to evaluate the one-loop determinant. That's not what we are trying to, what I'm proposing here. I'm rather proposing to work out something by just using the full geometry, never making explicit use of the fact that there is an ADS2 throat. Okay. It's also slightly different from the idea that has been employed to great success in computing the supersymmetric index for using gravity, where in the last 5-6 years, this has been employed in a wide variety of examples where the logic is slightly different. The logic is to use is to work with supersymmetric solutions, which are at finite temperature here being a misnomer. So these are complex Euclidean saddles, which are supersymmetric and satisfy boundary conditions that there is an asymptotic thermal circle with finite period, which shrinks somewhere in the interior. Okay. And this, for example, was important in the study of supersymmetric ADS5 black holes, but has also been applied to analyze the index computations for asymptotically flat black holes. So that's not also what we're going to try to do here. So I'll make two claims and justify them in the course of the talk. The two claims I'll make are that the near-horizon zero modes of extremal black holes generically live to light off-shell modes of the quadratic fluctuation operator around the near-extremal black holes. These off-shell modes have eigenvalues which scale linearly with the Matsubara frequency. And such modes can arise from a variety of gravitational and matter fluctuations. Almost always, such modes arise from gauge field fluctuations. They don't arise from ordinary matter fluctuations. There's always a graviton fluctuation that gives rise to what I will call the Schwartzian mode in the ADS2 throat. And this Schwartzian mode is responsible for this T to the 3/2 factor. In addition, there might be additional zero modes which depend on the geometry in question. Such zero modes could come from background gauge fields, like in Raster-Nordstrom from the Maxwell field, or they could come from background isometries. So again, in Raster-Nordstrom, there's an SO3 rotational symmetry, and there are associated zero modes through this rotational symmetry. Speaking of rotational symmetries, the zero modes are associated with rotational isometries appear to be subtle, especially when these are abelian rotational isometries in Ricci flat spacetimes. Okay, and one of the issues we encountered in our analysis was that we had an issue when we were analyzing the near-extremal Kerr black hole, where there was a expectation of a certain number of zero modes, including one associated with the rotation around the axis of Kerr. And we didn't find such a zero mode by working in a particular gauge, in a harmonic gauge. I'll explain what the subtlety is, and in particular, argue that the harmonic gauge breaks down in the near horizon region for Ricci flat spacetimes. Okay, so that's the sort of broad claims, and I will start out by first going through the analysis of the near horizon geometry and arguing where these temperature-dependent factors come from, and then upgrade the full story to the full asymptotically flat or asymptotically ADS geometries, as the case may be in some examples. Okay. Before I proceed, maybe I can pause to ask if there are any questions.
So what's the value added of considering the full asymptotically flat geometry as opposed to just the throat limit?
Well, as opposed to just the throat limit, I would say you might have wanted to ask the following question. Let me switch from asymptotically flat to asymptotically ADS and ask you, what in the boundary CFT is responsible for the low energy thermodynamics being changed? One answer you could give is, well, it's some collective mode that emerges in the infrared. But that collective mode is hard to see from the boundary CFT point of view because it's very deep inside the ADS2 throat. Having an answer in the full geometry at least allows you to figure out what fluctuations of the bulk modes should you be considering as responsible for this. I'll give you one more answer later, but for now, let me see if that satisfies you.
Yeah, I'm just curious because I would have thought all these subtleties having to do with the soft modes in the infrared should be near horizon effects and relatively insensitive to whether the throat opens out onto asymptotically flat space or it's just a throat all the way up to the UV.
Well, it's important for this discussion that the throat actually ends, that it's not an infinite throat, because the infinite throat actually has a genuine zero mode. In other words, it's important that it's nearly ADS2 and not just strictly ADS2.
But that has to do with the vicinity of the horizon, not the asymptotically.
I agree. I completely agree. Yes.
Okay.
Yes.
Okay. Thank you.
Yeah. Any other questions? Okay. So I'll just break up my talk into two parts because I was asked to review the older story about Kerr. I'll initially begin with the discussion of Kerr, and then explain what our problem was with the rotational zero modes, and then talk about the more recent work with how we find these modes in the full spacetime. Okay, so let's talk about the near horizon perspective. So I'm going to spend two slides basically just talking broadly about the gravitational evaluation of the gravitational path integral and the one loop determinant. So bear with me. So let me focus on gravity with zero cosmological constant for this discussion. And let's just talk about how we compute the one loop fluctuations around classical saddle. So I have Einstein-Hilbert action, maybe some boundary terms, maybe some gauge fixing terms. So the saddle analysis is as usual. You just find solutions to Einstein equations with those given boundary conditions and evaluate the on-shell action. To find the fluctuations, we'll do something simple. We'll pick something like a harmonic gauge. So the gauge fixing term is basically the thing that given in terms of the harmonic gauge fixing term. And then we evaluate the quadratic fluctuation operator. Okay. For spin 2 fields, by choosing harmonic gauge, you can show that the fluctuation, the Einstein-Hilbert plus boundary term plus gauge fixing term simplifies into this second quadratic functional, which is governed by a kernel, which is the Lichtner-Witz operator, the operator that maps spin 2 symmetric tensors to spin 2 symmetric tensors. Okay. Now, if you have this operator and we can construct its eigenbasis, it may or may not have zero modes, one can then just compute the determinant having constructed the eigenvalues, having determined the eigenvalues. But there's a cleverer trick that goes back 5-6 decades, but was exploited extensively in analysis, in this black hole analysis by Ashok Sen. And the idea is basically used to use the heat kernel technique, where you expand the quantum propagator in the eigenbasis of your fluctuation operator, and then extract from it the one loop determinant or the contribution to the one loop partial function. Now, this heat kernel, K, has UV divergences, but most of them, they just have to be counter-termed away. So all the power law divergence in the heat kernel, one just uses to regulate various couplings. There's however physical information in the piece of the heat kernel in K of S, which is constant, and it's present in even dimensions. Okay. Secretly, this is the statement that this piece knows about the conformal anomaly. And this piece can be extracted, as was analyzed by Christensen and Duff, by directly working out what the conformal anomaly is without actually constructing the eigenbasis. So assuming that, and further, if you further assume that the black hole saddle point configurations have only one macroscopic scale, namely, say, the horizon size, you can actually extract from this the one loop correction to black hole entropy. Okay. So at this point is important, so let me emphasize slightly what I'm saying here. So you know what the conformal anomaly is. This of course you can extract from basically evaluating things like Euler character or Weyl invariance on the black hole saddle. The non-trivial aspect here is to know that once you have evaluated that answer, that you have precise control on what the free energy, one loop correction to free energy is in terms of physical parameters. In the case of asymptotically flat black holes, there's only one physical scale. So once I set all my charges, fix all my charges, the black hole has some overall horizon size, and I can take that size to be large and scale all parameters to be large to be scaling with the same at the same rate. If, however, I have something like a cosmological constant, that being a Lagrangian parameter, it may not scale the same way. So I might be able to determine the answer up to some relative ratio of charges measured in ADS units or de Sitter units but not precisely that function explicitly. Okay, so in the case of asymptotically flat black holes, using this information, one can actually work out the logarithmic corrections to black hole entropy, which was the work that I mentioned was done by Sen about a decade and a half ago. So he had predictions back in the day for the Kerr black hole, and he had predictions for both the non-extreme Kerr black hole and for the extremal one. And the distinction being that in one case, one is evaluating in the latter case for the extremal black hole, one is evaluating the one loop answer in the neighborhood of t equals 0, so it's not analytic. It doesn't correspond to the previous answer for the non-extremal Kerr black hole. So for the Kerr black hole, there's a universal area over 4 g-Newton, the Bekenson-Hawking piece, and then there's a log correction with a coefficient in pure gravity. This is just for Einstein-Hilbert action, which is some number that can be determined from the conformal anomaly. For the extremal case, the new thing is the coefficient in front of the log is different, and that's the difference is attributed to the fact that there are 4 zero modes in the near horizon region. Okay? So the 4 zero modes of the gravitational fluctuations, which don't live to 0 modes in the full geometry, but they are there in the near extremal limit, so that changes the coefficient. This would seem to say the statement that the near extremal Kerr black hole still has macroscopic degeneracy. Maybe S0 was the degeneracy at 0 temperatures and for Kerr, it's simply given by the angular momentum parameter. So it's S0 is 2 pi j. And so you might have said, okay, so that an extremal Kerr black hole has macroscopic entropy. This is a small quantum correction once you account for logarithmic fluctuations of gravitons around this background, but that's what it is. This is not true. If one actually accounts carefully for the one loop determinant of the 0 modes, as I was saying earlier, then the actual entropy for Kerr black hole, and here I'll explain why my coefficient of log S0 is different, is the classical piece, a linear correction in temperature, plus importantly, this 3/2 log t piece at a scale determined by a quantum fluctuation scale, what I call t gap before, but for Kerr is given by 1 over j to the 3/2 in Planck units. Okay, and I should emphasize that this answer that I'm deriving is true for low temperatures, but not exponentially low temperatures. So it's true for t of order tq, but not t exponentially small compared to tq in units of S0. So it's not valid when t is tq e to the minus S0, okay, because we don't have control on what other gravitational saddles could contribute in that regime. Okay.
So Sen's answer is never the accurate result? Or is there a regime where it's appropriate?
Okay, I'm going to sidestep this question for now. I'll come back to this because there's an issue which I'm going to defer to the end of the discussion. Assuming your question pertains to Kerr itself. If it pertains to Reissner-Nordström, there will be a similar story. I would have said Sen's answer never applies. There's an issue with Kerr, and I want to defer that because it's a subtle issue.
Okay.
Okay.
Okay, is there a known exact result that's valid all the way down to t equals 0?
No. So the formula I'm showing you here is valid, is the correct formula when t roughly is bigger than tq e to the minus S0, and is valid up to roughly of order t, some temperatures of order tq, and then Sen's answer takes over because the gap modes become gapped. Does that help?
Yeah.
Yeah. I wrote an old formula here, and I intentionally wrote 154 over 180 for the coefficient of the log and not 64 over 180. And the difference in the factor is whether there are 3 zero modes or 4 zero modes. So when we did our calculation a year ago, we were able to justify the presence of 3 zero modes in the Kerr geometry, and they were sufficient to give us this t to the 3/2 factor that shows up as 3/2 log t here. But we weren't able to convince ourselves of the existence of the 4th zero mode. Now we do. So the correct form, there is no problem with the coefficient of log S naught. I just left the old formula here to emphasize that something we had missed in our first analysis. Okay, so this is the result. And now I'll tell you how we got here, and then I'll come back to the thing I promised Emil, namely the subtlety with Kerr. So what we're going to do is we're going to take the Kerr geometry and we're going to zoom in to the near horizon region in the extreme of the extremal black hole. So this was worked out in the late 90s by Bardeen and Horowitz. So this is the rotating analog of the Bertolli-Robinson solution, and it looks like a ADS2 fibered over a 2-sphere. So the rotation is buried in here. This part is ADS2, and there's a non-trivial warping of this geometry over the 2-sphere. Okay. Because of the angular dependence, because the fact that the ADS2 is not just fibered but also warped over the S2, I don't think it makes sense to dimensionally reduce down to ADS2. Okay. Nevertheless, should you want to do so by picking a particular ansatz, you would find a JT gravity-like theory with a dilaton whose profile depends on this angle and on the polar angle, theta. And you could do the analysis that I'm about to describe by just working in the ADS2 geometry. Okay, this was done in some of the earlier papers. Our point was that the only isometry here on which you can reduce is the phi angle, the azimuthal angle, and that would give you some effective 3-dimensional geometry which has nothing to do with JT gravity. Okay. So we're going to stick to the 4-dimensional near-extremal geometry and analyze what happens. In this near horizon limit, the natural boundary conditions are as follows. The geometry is asymptotically ADS2, and in asymptotically ADS2 geometries, you need to fix all the conserved charges. So in particular, we need to fix the angular momentum and not the angular velocity, as one would have done more naturally in the full asymptotically flat geometry. Okay. If I have time towards the end, I'll come back to the subtlety between what ensembles are defined where and explain them later. So what one expects is that there should be a set of universal zero modes coming from this ADS2 factor. There should be, roughly speaking, 3. By 3, what I really mean is there should be a discretum of modes with 3 modes missing because they're not normalizable, and they effectively contribute as 3 bosonic degrees of freedom to the one-loop determinant. Okay, and we'll see that in a moment. And so these would be what the modes I would call the Schwarzian mode. And they arise because of the SL2 invariance, which is broken when this near-extremal geometry, this throat of extreme Kerr, joins back into the asymptotically flat regime. So this was my earlier statement, that what matters is not so much that you have an infinite ADS2 throat, but rather at some length scale, this ADS2 throat opens up towards the asymptotic region. And as Emil pointed out, it doesn't matter whether the opening out is towards asymptotically flat spacetime or asymptotically ADS. So what we want to find is, and there should be another zero mode associated with the phi rotations, and so that should be therefore a net of 4 zero modes. So the strategy is basically we followed something very straightforward. We roughly knew what the zero mode should look like from the work in ADS2. So we guessed, and directly in this case, initially just solved the elements in the kernel of the Lichtenowitz operator. So the Lichtenowitz operator is the operator I had here, in basically the Laplacian minus Riemann tensor. And you can show, without too much work, that there exists a set of modes, which are in some sense the ADS2 analog, or in this case, near-extremal Kerr analog of the Brown-Hanno diffeomorphisms. Okay. So there's some function phi in this ADS2 space. And you can construct a vector field out of this function, which generates large diffeomorphisms. The metric fluctuations thus generated are in the kernel of the Lichtenowitz operator. And these are the genuine zero modes because they're generated not by small diffeos, but by large diffeos that affect the asymptotics of ADS2, which will matter when we are going to open up this throat into the full asymptotic geometry. Okay. The normalization of these modes in the space of fluctuations for computing the functional integral is the ultra-local measure. So basically just metric fluctuation, dotted metric fluctuation in the background metric measure. Okay, so this is the explicit form for the diffeomorphism, and one can work out what the metric fluctuation looks like. To compute the one-loop determinant, there's a nice strategy. So in this extremal black hole, the modes I've written at the bottom are genuine zero modes. So they have zero action, and therefore they should not be treated classically. They're strongly coupled from a quantum mechanical point of view. Okay. What one can do is to gap them a little bit so that one can compute their determinant. And one way to gap them is to basically turn on the temperature. So we'll go to the near-extremal solution and zoom in again to the near horizon limit. Okay. So in particular, I'll write down the metric of the full space of the spacetime as the extremal metric plus an order T correction. So this G0 plus TG1 will satisfy Einstein's equations to order T in some neighborhood of the horizon. Okay. This is not asymptotically ADS2 because G1 will have deviations that are irrelevant from the ADS2 point of view. The H mu nu, the metric fluctuation, is basically the fluctuation that's obtained from this diffeomorphism, the Schwarzian diffeomorphism. It's a zero mode on G0, but it's no longer a zero mode on G1. So when you evaluate the quadratic flux operator for this regulated metric, you will find that now these modes, the set of modes coming from this set of diffeomorphisms parameterized by an integer n, pick up a non-trivial action and the action is clearly proportional to temperature because as temperature goes to zero, these are zero modes. But now you have a collection of modes whose determinant you can compute because now it's just a Gaussian integral over the amplitudes. Yes.
Why is that? This is probably a stupid question, but in your killing vector, why is there phi dependence at all? Why is there a DD phi term at all?
Yes, yes.
Is to killing modes?
No. So this is a good question. So you might have thought that the modes are basically just the modes in ADS2. Right. So if I didn't have the phi, if I didn't have the DD phi piece, you might have thought that it's just like as if you were doing something in ADS2. But realize that when you, okay, I'll explain it in two different ways. So imagine you dimensionally reduce from this 4-dimensional geometry on a particular ansatz, which I don't like, but let's do it anyway. And you get ADS2. But what you will get in ADS2 is a SL2 gauge field, y minus 1 dt, coming from this fibration. Okay, forget the warping for a second. If you do a diffeomorphism in ADS2, the gauge field will also transform.
Oh, I see.
Okay, so that's that piece. It's basically the fibration piece that tells you that you can't just do a diffeo in just the ADS2. You also have to compensate for it with a angular dependence.
Yeah. Good, thank you.
Could all of this be phrased in some language of consistent truncations and some statement that you can't just consistently truncate the geometry to ADS2, but you also need some soft phi modes?
Yes, definitely. You can say it that way. But in this case, I would say that there is just no truncation because of the warping. Because it's theta dependence. So
Yeah, no, but that just means there's some higher L modes that you need. That consistent truncation just doesn't mean eliminate all theta dependence. It means keep some particular spherical harmonics in the
I agree, but I agree, but it involves keeping very particular modes that respect this ansatz, which at least I don't know how to justify.
Okay.
It turns out to be true, but I don't know how to justify from first principles.
Okay.
Okay. So I won't derive the on-shell action for you, but take my word for it. 2 pi j is easy to see, just the Gibbons-Hawking answer for the extremal case. T squared over T over TQ is the correction that comes from having turned on the temperature and kept the linear T piece. The new piece is this epsilon squared piece. Now, the way I wrote this, these modes seem to exist for any integer n. But if you stare at my formula for phi for a second, you will see that the modes with n equals 0 and plus minus 1 actually are not normalizable with respect to this ultra-local measure. So in the space of fluctuations, in the space of vector fields that which generate these Schwarzian modes, n equals 0 and plus minus 1 are missing, which is why my sum here runs from n greater than 1. Now, the integral over epsilons with respect to the ultra-local measure is Gaussian, so it gives you some factor of square root Tn. And you have to take the product over all values of n with three modes missing, 0 plus minus 1. And if you sort of zeta function regulate that product, you will find that that gives you precisely T over TQ to the 3 halves. Okay. So this is the contribution from the Schwarzian modes. And as promised, this reproduces the 154 over 180 log S naught is not a new calculation. This is basically the calculation that was done by Sen. The new piece is just the last piece in this. Let me pause here to check if there are any questions about this piece of the calculation. All right. So then let's talk about what we expect. We expect one more zero mode, namely the one associated with rotations. And for reasons that Sav just asked, you might worry whether we already took that into account. Okay. Going back to the same intuition of doing the dimensional reduction, we have an abelian gauge field. And now you can imagine being able to do a large gauge transformation for this abelian gauge field in this asymptotically ADS2 geometry. And in fact, for Maxwell theory in Reitzer-Nordstrom, this the gauge transformation by this function h would indeed be a large gauge transformation. So we can take this function and the large gauge transformation for this dimensionally reduced gauge field basically is a Diffio in 4 dimensions for a rotational killing vector for a vector which is basically this function times the rotational killing vector. You can compute. I ask whether the Diffio that it generates, the metric fluctuation it generates by Diffio, whether it's in the kernel of the Lichnovitz operator, and you find it's not. And in fact, it's not hard to see that the reason it's not is simply because the gauge condition is not being respected. After all, I'm doing a Diffio, so it better preserve the fact that I'm not doing any. It shouldn't be changing the background curvatures. So what surprised us more was that you might say, okay, fine, this was just some choice of a killing field of a Diffio, but this is a particular choice of parameterizing a large diffeo. Maybe what we should do is do a compensating small diffeo to bring us back into our gauge fixing choice. And our original conclusion was we can't do it. I'll explain why. And we decided that, therefore, they don't appear to be zero modes associated with such large diffeos. And if that were true, then in the canonical ensemble, the log area term would have a different factor than what was predicted 10 years ago. But importantly, it does not affect the temperature dependent piece. And this I will explain once I explain the nature of this diffeo in a second. Okay, so hang on to this point, because the two effects that zero modes do bring in. One is what correction do they do to the Bekenstein-Hawking entropy, which is temperature independent. And second, what temperature dependent piece do they give to the Bekenstein-Hawking entropy? So, as I said, this was the puzzle we had in our paper from 2023. Thanks to Maciek, we tried something else. We basically tried doing the same analysis for Kerr radius 4 or Kerr Newman solution. And surprising to us, we found that there actually was a zero mode, which in fact was in harmonic gauge. And if you have Kerr Newman, then you also want to make sure that the diffeo doesn't take your Maxwell field outside your chosen gauge. So we picked Lorentz gauge for the Maxwell field, and it respected that as well. So let me convince you in the following, that the problem here is the breakdown of the harmonic gauge condition for Kerr. So I'll remind you that the harmonic gauge fixing functional is basically the gradient of the metric fluctuation after partial trace removal. And a zero mode exists if it's generated by a large diffeo, as that's what we are trying to find. And in fact, we were trying to find it by this particular diffeo that I talked about moments ago. Now, as I said, again, when you have a large diffeo, which is not in the your gauge of choice, you can perform a compensating diffeo. But now this compensating diffeo will bring you back to your favorite gauge, provided there's a solution to some elliptic inhomogeneous equation. So in this case, if you can work out that the compensating diffeo needs to satisfy this second order PDE given by Laplacian plus the Ricci tensor. And the source is basically the gauge fixing functional that was non-zero. Should we not be able to satisfy our gauge condition, then it basically says that this elliptic operator appearing on the left-hand side itself has a non-zero kernel. So you can't invert it. And for Ricci flat backgrounds like Kerr, you can show that but this particular operator, in fact, has a zero mode. And this is the issue why we couldn't bring back the perturbation into harmonic gauge. Okay, so what this means is that if you're actually fixed harmonic gauge, you can also check that this particular operator, and I'll have a formula later in the slides, is also the kinetic term for the ghost, for the diffeomorphism gauge fixing. Which means that the ghost kinetic operator in this harmonic gauge, because this elliptic operator has a kernel, also has zero modes. So if one wants to analyze the perturbations of near-extremal Kerr in harmonic gauge, one not only has to worry about what's happening with metric fluctuations, but also with the ghost determinant, and that's not something we had done. And the argument I'm giving you here, I haven't written all the details. It's very easy to check that one can construct such. Basically, for Ricci flat backgrounds, the operator in question is just a Laplacian acting on on one forms, and using the eigenmodes of scalar Laplacian and ADS2, you can always construct some element in the kernel of this operator for Ricci flat backgrounds. And the reason there was no problem with Kerr ADS4 or Kerr Newman is that they're not Ricci flat. So the operator doesn't have such zero modes. Okay. So with that in place, the story for Kerr works out. You get the log corrections giving you this 64 over 180 to the log area term. There is a zero mode associated with rotations. However, in the ensemble with fixed angular momentum, that zero mode does not contribute. Okay? I'll come back to this point in some detail and explain why that's the case. But for now, I will insist that the discussion about when zero modes contribute depends on ensemble choices. The Schwarzian mode always contributes, but other modes associated with isometries or gauge symmetries may or may not contribute depending on what ensemble and what boundary condition one chooses to impose. So I'm fixing J and temperature, and with those fixed J and temperature, the correction is T to the 3/2. Okay. Now, let me pause for 2 more seconds to ask if there are questions, because then I'll answer Emil's question about Kerr. Okay. So are we done? Are we sure that the black hole thermodynamics formula for Kerr is the formula I've written down here? The entropy is basically given by this formula with this 154 replaced by 64. And I claim not quite. There's one more subtlety. So we just looked at the near-extremal Kerr black hole and focused on these nearly gapless modes. And we just computed the one-loop determinant around the saddle. There's a problem, however. Kerr famously suffers from superradiance instability, and which means that in addition to the piece we've computed, the one-loop effective action also has an imaginary piece. And this therefore says that the black hole has a decay timescale. And if you estimate the decay timescale, basically from just asking how long it takes for a black hole to evaporate, that time scale is comparable to the scale at which these quantum effects set in, and the scale is basically set by angular momentum, it's set by this TQ parameter. Okay, so 1 over J to the 3/2 is roughly the same scale at which superradiance is important. So now there's a competition and of the following kind. You might focus on the near-extremal Kerr black hole and try to compute its thermodynamics. But the question is, does near-extremal Kerr black hole stay in that near-extremal regime where analysis is valid long enough for us to be able to trust these one-loop determinants? If the black hole superradiates and becomes further away from extremality, then we won't have to worry about these quantum corrections. Okay, so this, the back of the sort of the basic point was pointed out to us by Malasena and Murthy after our paper, but none of us has sat down to carefully reanalyze whether the one-loop determinant, there exists a regime for Kerr where this one-loop calculation is going to significantly affect thermodynamics. Okay, so this is something we are thinking about, but I don't have an answer for you today. There's a similar statement that one can make about superradiance in Rice-Nordstrom, and this was analyzed in a recent paper by Jeff Pennington, Luca Iliescu, and collaborators, but we haven't sort of translated some of those statements into Kerr, and there are some subtleties with directly applying them in this case. So hopefully that answers your question, Emil.
Mm-hmm.
This issue does not persist for Rice-Nordstrom, especially when you have modes because there you can tune charge to mass ratio of fields. And if you're just talking about Einstein-Maxwell theory, then there is no problem. Whereas in the case of Kerr, since graviton static spin, there is no tuning parameter left. So everybody is order 1, and you have to be very careful whether the quantum effects are indeed reliable in light of superradiation. So I would rephrase our statement and say we have a prediction for the absolute value of the one loop determinant, but don't have a statement about the imaginary part. Okay, so I have about 10 minutes left. So let me say a few things about going beyond the near horizon and showing you some general results, which about how these modes, which I just described for you in the near horizon, lift off into the full geometry. I'll do something simple first and then give you some numerical results for Rice-Nordstrom. So simple thing is to look at the BTZ geometry, which I've written out here in 3D asymptotically ADS3 spacetime. Details are not important. And so again, what we'll do is we'll look at the fluctuation of spin 2 fields in the full geometry. So I'm going to be working in the full BTZ geometry. In this case, it doesn't even matter. One can study the fluctuation of the these metric perturbations in a fixed gauge. Okay, maybe I should say something here. This is ADS3, so there are no physical gravitons. Okay, so what I'm going to do is I'm going to gauge fix, in this case to harmonic gauge, and look for eigenmodes of the quadratic Lichnovitz, spin 2 Lichnovitz operator. Okay, whether they how they contribute to the one loop determinant and so on, I'll explain later. And again, I've written out the gauge fixing term, and in this case, I've had explicitly written out what the ghost action is, which you can see is basically the same operator I had in my previous analysis of the rotational zero. Okay, so now the geometry is nice because it's ADS2 fibered over a circle. There is no warping factor. So in fact, the geometry is more or less like the Kerr geometry, except that you just set these functions of theta to, roughly speaking, 1 and drop the theta dependence. Some factors, but. And here you can just solve for the eigenfunctions for the Lichnovitz operator, which are transverse traceless spin 2 tensors. And here's the answer. Okay. This is the full eigenspectrum of the spin 2 of the Lichnovitz operator. So I've written the answer in terms of the left and right temperatures, which are combinations of inner and outer horizon radii. And you can see that the formula is generally nonlinear in temperature, but as I take the left temperature in my parameterization to 0, the eigenmodes have eigenvalues which scales linearly with the Matsubara frequency. Okay, so in fact, the eigenmodes are basically n times temperature in the limit when I go to the in the extremal limit. Extremal limit is TL goes to 0, TR finite. And this you can work out even the explicit eigenfunctions. There are some simple simple profile in terms of elementary functions. But what's nice is that you can actually see where these modes are supported. So here's a plot of the modes as a function of proper distance from the horizon. And you see that as you lower the temperature, the modes get pushed further and further down the throat. And basically, the wave function profiles eventually on the nose match on with those of the Schwarzian mode, the analog of what I showed you for Kerr, but for BTC. Okay. And again, the 3 of these modes, n equals 0 plus minus 1, are not normalizable and excluded from the analysis. Let me skip this for now and just show you something similar for Rice-Nordstrom. So for Rice-Nordstrom, we were not able to, of course, solve for the eigenfunctions of the Lichnovitz operator explicitly, but what we expect is a set of Schwarzian modes associated with gravitons, a U1 gauge mode associated with the Maxwell field, and rotational zero modes associated with the transverse spherical symmetry. And for simplicity, we sort of work this out in the context of Rice-Nordstrom ADS, where the cosmological constant provides a natural IR cutoff to make boundary conditions easy to implement in numerically for. So you can check that in each of these three cases, these are perhaps the most instructive boring plots that I have seen. They're linear plots, but they're plots for low temperatures for the eigenvalues of the appropriate fluctuation operator. And you can see the modes come in families, and the eigenvalues are all proportional to the Matsubarra frequency, some order 1 coefficient, which basically says what TQ is. And this is for the graviton fluctuations of Schwarzian modes. There's a similar statement for U1 modes and for the rotational zero modes. Okay. And again, one can check that these modes are concentrated down the throat, and the dynamics is very much, but they have some tail that allows you to sort of extract them in the full geometry. All right. So now I can explain the statement I made earlier about the nature of ensemble choices and what, when do these modes contribute to the one-loop determinant. So let's take Rice-Nordstrom, for example. So we just said that we have the Schwarzian modes from graviton. So that basically means 3 bosonic degrees of freedom. A U1 gauge mode, so that's 1 bosonic degree of freedom. And an SO3 family of modes associated with rotations, that also roughly means 3 bosonic degrees of freedom. And each bosonic degree of freedom gives a factor of t to the 3/2 if it's a zero mode from the Gaussian integral. So you might have thought that what you actually get is a 3/2 from the Schwarzian, a 3/2 from 3 rotational isometries, and 1/2 from U1. Okay. This is correct, but this is correct in the full Rice-Nordstrom geometry around a single saddle. In an asymptotically flat geometry, the right boundary condition to impose is to demand that you have a thermal circle of some period for the Euclidean path integral. But asymptotically, you can't fix the gauge charge, the Maxwell charge, or the angular momentum. What you can fix are the chemical potentials and angular velocity. Why is this? It's because the Coulomb tails associated with the charge, they are normalizable. Whereas the non-normalizable modes, which are the things you need to fix at infinity, are those associated with the chemical potentials. Okay. There are some subtleties if you're in ADS and in low enough dimensions of ADS, like ADS 3 or ADS 4. But this is asymptotically flat, and the only boundary condition that's allowed is fixing chemical potentials. However, fixing chemical potentials has to be done with care, because once you fix chemical potential, let's say charge chemical potential mu, the functional integral, the trace over e to the minus beta h, e to the minus beta mu, is invariant under shifts of mu by integer multiples of 2 pi I in units of temperature. Okay? Because this doesn't shift anything to it's the same trace in the Hilbert space. So what one is supposed to do if one wants to get the actual answer in the grand canonical ensemble is to sum over a set of saddles labeled by this integer n, and then do the Legendre transform to get back the answer if you want the answer for the fixed charge ensemble. Okay. So once it's expected, although as far as I know, not proven in the case of Rice-Nordstrom, that each of the saddles could give you a different answer, because the chemical change of chemical potential at infinity will change the geometry. But they will all give you this t to the 3/2 because one expects that they will give you these temperature dependent factors. But the sum over saddles effectively kills the contribution from everything but the Schwarzian mode. So the prediction, one that I think needs more careful verification, at least for Reissner-Nordström, is that the contribution always only comes, the temperature contribution in the canonical ensemble with fixed charges always only comes from the Schwarzian and not from other zero modes associated with rotational isometries or gauge fields. Okay. And I think in light of time, I won't go through this. I will say one last thing which is related to BTZ. In the BTZ case, you can, so this is the near horizon metric. And in addition to the Schwarzian mode, there's also a rotational mode, just like there was for Kerr. Okay. Now here we find that these modes do not extend to the full spacetime because all the eigenmodes I showed you before for BTZ are all there are in the geometry. Secondly, this being BTZ, one can do an analysis in conformal field theory and use holography to predict that the one loop determinant is T to the 3/2 in both canonical and grand canonical ensembles. So in particular, it's the same answer even before doing the sum over these shifts of chemical potentials. And the final point I wanted to say here is whether or not, I made the point that whether modes contribute depends on ensemble, but there's another factor which depends on whether modes contribute. The other factor is whether the susceptibility associated with these fluctuations is vanishing or not. Okay, so the scale at which the Schwarzian modes contribute, this gap scale, this TQ scale that I use for Kerr, is roughly speaking set by the specific heat of the black hole at extremality. So it's basically the rate of change of entropy with respect to temperature with fixed charges at zero temperature. For the gauge field and rotational zero modes similarly contribute depending on whether the charge susceptibility or the angular momentum susceptibility is non-zero. Should these susceptibilities be should they vanish, then such modes won't contribute. In BTZ, the extremal BTZ is a solution that rotates at the speed of light, and its angular velocity is fixed to be 1 in ADS units. And therefore, you can, there's the angular momentum susceptibility for BTZ is 0. So the rotational zero mode doesn't contribute because it's not normalizable in the near horizon geometry. And we can check this explicitly. And we just, as I said, we didn't find analytically any solutions to the quadratic fluctuation operator which can be associated with rotational zero modes. This has an implication for Reissner-Nordström, which is why I wanted to end on this point. The charge susceptibility for Reissner-Nordström is also vanishing because the chemical potential for Reissner-Nordström in asymptotically flat space is, charge susceptibility is divergent. The chemical potential is constant, independent of charge. And we find from our numerics that the plots I showed you, that if you try to take the eigenvalues for the gauge field fluctuations, they scale like Matsubara frequency, all right, but in the extremal limit, they blow up and they're not normalizable. So this factor of mu-1 is basically a statement that with appropriate normalization, right, the chemical potential for extremal Reissner-Nordström is unity. And in the extremal limit, the gauge field zero modes don't contribute. Okay, so let me sort of end here. So I showed you two things. One which is about the explicit analysis in the near horizon region for Kerr, but also how modes in the near horizon live to the full geometry. I only showed you these results for BTZ and Reissner-Nordström. We have some results for the hyperbolic ADS black holes. None of us have been brave enough to try to do this analysis numerically for Kerr, but I think in principle it should be doable. At least Maciek should be able to do it. And I'll just make a couple of statements that the results that we obtained, they hold not just in semi-classical gravity, but they also hold in semi-classical string theory. And I'll end with a comment that the one-loop determinant I computed was by basically either looking in the near horizon, computing some contribution from some special set of modes, which were gapless in the extremal limit, and then using small temperature to regulate their on-shell action and computing their effect at small temperatures, or working in a full geometry at small temperatures and identifying a set of eigenmodes of the appropriate quadratic fluctuation operator. There is a curious formula, in fact, an interesting formula, which is an application, is a, what should I say? Corollary of something called the Gelfand-Yaglom theorem, which gives a formula for the one-loop determinant around black holes in terms of quasi-normal modes. So roughly speaking, it's a product over quasi-normal modes minus Matsubara frequencies, and it includes both the quasi-normal modes as poles of the retarded Green's function and also the anti-quasi-normal modes, which are poles of the advanced Green's function. This was put forward about a decade and a half ago by Denef, Hartnell, and Sachdev. And you might ask, can you see the temperature dependence from this formula? So recently, this formula has been used to derive the log corrections. I unfortunately didn't forget to put that reference. But in the case of Kerr, this paper by from around Christmas showed how to use some beautiful results from about a decade ago for the eigenspectrum of quasi-normal modes for near-extremal Kerr to basically rederive this T to the 3/2 directly from this formula. Okay, so and the question is, can one say something more general? They mostly establish the fact that you can use this determinant formula to get the prediction that's not now understood, but you might think that there's a more general story one can say. That's something I'm thinking about with Frederick Gia. Okay, let me stop there, and sorry for going slightly over time.
Any questions for Mukund?
Is there an intuitive picture for why the one-loop determinant can be expressed in terms of quasi-normal modes?
Yes. So let me try to see intuitive picture. There's a sort of, the argument that these guys use is roughly speaking the following kind of argument. You say, you see, think about solving the problem with some fixed boundary conditions at infinity. So let's say for example, we're in ADS, okay? So you fix non-normalizable boundary conditions at infinity. And then you try to solve for ingoing modes. Now, if you switch off the non-normalizable modes, if you switch off the non-normalized boundary conditions and ask for solutions that are purely normalizable, then those will be the physical quasi-normal mode. They're normalizable at infinity and ingoing at the horizon. So what you can try to do is write down as a differential equation statement. You can say you have some determinant of some operator and extend that operator, if you like, into complex domain. And then ask where are its zeros and poles. And from this, by basically running what I just said of starting with turning on non-normalizable boundary conditions and then turning it down back to normalizable, you can argue that the poles or zeros of this determinant formula should be at the quasi-normal frequencies. That's a heuristic, and that was basically the heuristic. A formalized version of that heuristic was what Denef, Hartnell, and Sachdev gave in their paper. I think there's a slightly more nicer mathematical physics statement that basically uses something about determinants of appropriate operators, and that determinant can be written in terms of on-shell solutions. But not sure I fully answered your question.
That gives me an idea. Yeah, thank you.
Any other questions? If not, let's thank Mukund again.
Right. Thanks. So
Thank you, Mukund. Happy New Year.
Happy New Year to you. Bye, folks.